It seems like every day there's a new headline about some major cyber attack. And the thing is, they're not getting any simpler. It feels like organizations are fighting an uphill battle against attackers who might already be lurking within their systems.
You hit the nail on the head there. Perimeter security is still crucial, but the truth is, determined attackers often find ways to breach those defenses, and that's where assumed breach penetration testing becomes so important.
Okay, so instead of just checking if we can be attacked from the outside, assumed breach testing flips the script. It starts by assuming an attacker is already inside, and it focuses on what they could do from there. Seems like a much more relevant approach, wouldn't you say, given the threats we face today?
Absolutely. It shifts the focus from that initial prevention to understanding the potential damage an attacker could cause once they've bypassed those first lines of defense. It's about seeing how far they can spread within a network, what sensitive data they can access, and whether they can achieve their ultimate objectives. Things like taking control of critical infrastructure or stealing valuable intellectual property.
Right. But traditionally, these really in-depth penetration tests, the ones that truly try to mimic a sophisticated insider threat, they require a lot of expertise, right? Experienced security professionals who know all the ins and outs of these attacks. And that expertise comes at a price.
Precisely. You need individuals with a deep understanding of network architecture, various attack methods, and the ability to connect the dots between seemingly minor vulnerabilities to create a pathway for a significant breach. That level of skill is in high demand, which makes it expensive. And the thoroughness of these tests often means they take a considerable amount of time to complete.
Which brings us to a fascinating possibility. What if we could leverage the power of AI, specifically these advanced large language models, to automate parts of this process? Could an AI actually learn to think like an attacker who's already inside a network and figure out how to exploit its weaknesses?
That's the core question we're diving into today. Researchers have been exploring the use of LLMs for automating penetration testing, and there have been some interesting developments. But a lot of this work has been limited, either partially automating the process or focusing on attacks against single computer systems.
But the research you shared with me takes this step further, right? It explores a prototype designed to see if LLMs can autonomously conduct these assumed breach simulations within complex enterprise networks, specifically targeting Microsoft Active Directory environments, which are incredibly common.
That's exactly right. The team behind this research wanted to see if an LLM-driven system could successfully compromise user accounts within a realistic Active Directory testbed. They weren't just looking for known weaknesses. They were simulating a full-blown multi-stage attack, starting from reconnaissance and moving all the way to potentially gaining domain admin privileges.
So the big question we're tackling today is this. Can these LLM-powered systems genuinely hack into enterprise networks on their own? And if they can, what are the potential consequences? We also want to delve into some of the unexpected discoveries the researchers made when they put this prototype to the test.
Let's jump right in. The fundamental question the research addresses, as you highlighted, is whether an automated LLM-driven assumed breach simulation is a feasible and effective method for compromising enterprise networks. It's a bold idea, and the researchers tackle it head-on by developing a pretty sophisticated prototype.
Tell me a little more about this prototype. What were its key features?
It's essentially an autonomous system that uses large language models to try and compromise accounts within a simulated but highly realistic Active Directory environment. The researchers focused on automating the essential phases of a penetration test, aligning with the ITAR ATT and CK framework. So they aim to cover reconnaissance, gaining that initial access to credentials and basic discovery within the network, with some initial steps towards moving laterally.
So it wasn't just randomly executing commands, it was following a structured approach, much like a human penetration tester would.
Precisely. And to really test the prototype's effectiveness, they needed a test environment that accurately reflected the complexities of a live enterprise network. That's where Game of Active Directory, or GOAD, comes in.
GOAD, I have to admit that's a pretty patchy name. What exactly is it?
Imagine a realistic simulation of a vulnerable Microsoft Active Directory network. What makes GOAD so valuable is that it's designed with complex interactions between different systems, what we call stochastic outcomes. This means things don't always happen in the same predictable way every time you run it, which is a hallmark of real-world uncertainty. It also includes critical timing dependencies. All of these elements are things you'd encounter in a real network, and they're essential for evaluating how effective an automated attack system could be. And of course, they focused on Microsoft Active Directory specifically because it's so widespread in enterprise settings and, unfortunately, a very common target for attackers, especially when it comes to things like ransomware.
So it's not some simplified artificial setup. It incorporates the messiness of a real network. So how did this LLM-powered prototype actually try to break into this GOA environment? What were the main stages?
In a nutshell, the prototype automates the penetration testing process by using LLMs to plan and execute attacks. They emphasize one particular attack chain that involves something called ASREP Kerberos roasting. Now, this is a technique used to obtain password hashes for user accounts that don't require pre-authentication. Once the prototype had these hashes, it would then try to crack them using standard password cracking tools. This is just one example, but it illustrates how the system could link together different attack techniques to achieve its objectives.
So it's not just identifying a single weakness, it's exploiting one vulnerability to gain a foothold and then using that access to search for further vulnerabilities, much like a human attacker would operate.
Exactly. And the researchers emphasized that this prototype was the first fully autonomous LLM-driven framework that could successfully compromise accounts within this kind of realistic Active Directory testbed.
That's a pretty significant accomplishment. Now, before we get into the nuts and bolts of how it works and what they found, the paper does touch on ethical considerations, which is obviously important when discussing automated hacking tools. What were their key points?
They acknowledged the dual-use nature of any security tool. It can be used for both good and bad, right? For defense and offense. Consistent with the broader security community's principles, they strongly advocated for transparency and making their work open source. They believe that publicly releasing the prototype's source code, the detailed logs from their experiments, and their analysis ultimately enhances overall cybersecurity. It allows other researchers and security professionals to examine it, learn from it, and potentially develop defenses against similar attacks.
That makes a lot of sense. Openness can lead to a better understanding of threats and ultimately stronger defenses. Okay, let's get back to penetration testing itself. The paper outlines different types. Can you give us a quick rundown and tell us where this research fits within those categories?
Sure. They describe a few main types. First, you have vulnerability scans. These are typically automated tools that search for a wide range of known weaknesses, but they're often quite noisy. They're easily detectable, and they generally don't actively try to exploit the vulnerabilities they find. Their main goal is broad coverage, not deep exploitation.
So it's like a quick check to see what's visibly broken, right?
Exactly. On the other end of the spectrum, you have red teaming. This is much more focused, in-depth, often simulating a specific threat actor's tactics. Red team is usually very stealthy to avoid detection, and the objective is to achieve a very specific goal, not necessarily to find every single vulnerability. It's typically a manual process.
Like a covert operation with a specific target in mind?
Precisely. And then somewhere in between, you have internal network tests, which are often called assumed breach simulations. This is where this research fits in. In these tests, the tester starts from within the network, assuming that an initial compromise has already happened. The goal is often to achieve domain dominance in an Active Directory network, essentially gaining the highest level of administrative control. These tests try to balance breadth, identifying multiple vulnerabilities with depth, figuring out how to chain them together to achieve a significant impact.
So this LLM prototype is specifically focused on automating that middle ground, the assumed breach scenario within an Active Directory environment. Now, there have been other attempts to use AI for penetration testing, right? The paper mentions a couple. What were their limitations and how does this research differ?
Yes, they mentioned Pentest GPT and Hacking Buddy GPT. These were certainly steps in the right direction for automating parts of penetration testing, but they had limitations. They often only partially automated the process, or they primarily focused on attacks against a single computer system. This new work is different because it tackles the much more complex challenge of a multi-host network, where successful attacks require understanding the relationships between different systems and chaining together vulnerabilities across those systems.
So it's moving beyond individual machines to think about the network as an interconnected whole. LLMs have become pretty good at planning tasks. How did the researchers leverage that in their prototype?
They built on recent advancements in how LLMs can handle both single complex tasks and break down larger tasks into smaller, more manageable subtasks. For a single task, techniques like chain of thought prompting, where the LLM explains its reasoning step by step, and frameworks like React, where the LLM can interact with external tools, have shown great promise. Then for planning across multiple steps, there are approaches like plan and solve and the concept of Pentest task trees, which they actually used in their prototype. These allow the LLM to develop a high-level strategy and track its progress as it goes.
Okay, you mentioned Pentest task trees. Those sound important. Can you explain how the prototype actually used them?
The prototype has two main components, a planner and an executor. The planner is driven by an LLM called O1, and its job is to create and manage this Pentest task tree, or PTT. Think of the PTT as a dynamic to-do list for the penetration test. It outlines the steps the prototype should take. The planner uses the O1 model for that high-level strategic thinking, deciding what the next course of action should be.
Okay, so the planner is like the mastermind. What about the executor? What does it do?
The executor uses another LLM, GPT-4o. Its job is to take those tasks defined by the planner and actually carry them out. It does this by selecting the right commands on a Kali Linux virtual machine, which is a common platform for penetration testing tools. So it runs those commands and then analyzes the results.
So it's like a two-part system. The planner makes the plan, and the executor is the one that gets its hands dirty trying to execute that plan. How do they communicate with each other?
They work in a continuous loop. The planner updates the Pentest task tree based on the information it receives from the executor about the outcomes of the commands that were executed. It then analyzes the updated PTT, figures out the most promising next task, and sends that past, along with any relevant context like usernames or previous findings, to the executor. The executor then generates and runs the necessary commands, and the whole cycle repeats.
And all of this is happening within their virtualized experiment environment, right? With the GOAD testbed, the Kali Linux attack VM, all controlled by the prototype running on a separate machine. You mentioned they chose specific LLMs. Why those particular ones?
They chose OpenAI's O1 and GPT-4 models because they're generally considered to be at the forefront of LLM technology. They're often used as industry benchmarks. By using these models, the researchers know their findings would be easily comparable and remain relevant as new models are developed. They also build their prototype, which they named Cochise, using LangChain, a framework specifically designed to make it easier to integrate different LLMs. So in theory, you could swap in other models if you wanted to.
Makes sense to use well-established tools. Now, you mentioned the Kali VM, and it sounds like its configuration was important as well. They made some specific changes to it, didn't they?
Yes, they tweaked it to optimize it for automated testing. They enabled root login over SSH and increased the maximum number of simultaneous SSH connections. This allowed them to run multiple commands in parallel, which is important for efficiency. They also disabled the graphical user interface since their system wasn't designed to interact with it visually. Those are pretty standard adjustments for this kind of testing.
And it seems like they also made some changes specific to the GOAD environment.
That's right. They configured the DNS server on the Kali VM and added some backup mappings of server IP addresses, something a real attacker might do to ensure they can still communicate even if some systems are down. They also preloaded a list of potential usernames, taking inspiration from a walkthrough of an earlier version of GOA, using publicly available information. This list could then be used for attacks like ASREP roasting or password spraying.
So they're trying to simulate that initial information gathering that a malicious actor would perform. Now, you mentioned GOD is continuously updated. That raises the question of whether the LLMs might be using prior knowledge of GOAD's vulnerabilities. Did they address this potential data contamination?
They did. They acknowledged that since GO8 is publicly accessible, there was a chance that information about its specific vulnerabilities might have ended up in the LLM's training data. To investigate this, they carefully analyzed the logs from their experiments, looking for what they called non-causal attack flows. This would be evidence of the LLM taking shortcuts, like directly using a known GO8 password without going through the necessary reconnaissance and exploitation steps. They reported that they didn't find any instances of this in their logs, so it seems like the LLMs weren't just relying on pre-existing knowledge of the testbed.
That's good to hear. It means the LLM was genuinely learning and applying attack techniques, not just recalling specific GO8 vulnerabilities. They also use a consistent scenario prompt for the LLMs, right? What kind of instructions did that prompt include?
The scenario prompt was designed to put the LLM in the shoes of a professional penetration tester, someone hired to secure a Microsoft AD enterprise network. It told the LLM to use established methodologies like the Lockheed Martin cyber kill chain or the Mandiant attacker lifecycle when planning its attacks. It also gave the LLM a specific target IP address range to work with and excluded certain management IP addresses that were off limits. It reminded the LLM of the limitations of the Kali VM, like only using the designated network interface and avoiding any graphical or interactive programs. Importantly, it explicitly told the LLM not to use automated vulnerability scanners like OpenVAS. probably because configuring those effectively can be pretty time-consuming.
Makes sense to focus on more targeted attack methods. What about password-based attacks? Were there any specific guidelines for those?
Yes, they instructed the LLM not to perform online brute force attacks within the target network. This was to avoid triggering account lockouts, which is a responsible practice even in simulated attacks. But they did give the LLM access to the rockU.txt word list, a list of commonly used passwords, and allowed it to crack any password hashes it captured offline. They also encouraged the LLM to generate its own scenario-specific password and user lists based on the information it gathered during the test.
So, more intelligent guessing and offline cracking rather than just throwing a ton of passwords at the wall and seeing what sticks. It sounds like they also included some tool-specific guidance in the prompt to help the LLM avoid common errors. Can you give an example of that?
Sure. One example is the tool Crackmatexec. It's been updated recently and is now mainly maintained as netexec. Both were installed on the Kali VM, but netexec is generally more stable. So they explicitly told the LLM to use netexec and gave it some basic instructions on how its parameters worked. They also pointed out that tools like nmap and netexec can take multiple targets separated by spaces, not commas, which is a detail that can trip people up. And they reminded the LLM of the specific naming convention for tools in the Impacket suite on Kali Linux. Those tools all start with Impacket. These might seem like minor details, but they can really help the LLM use the tools correctly.
Those sound like important guardrails, helping the LLM navigate the complexities of real-world penetration testing tools. Now, we touched on why they chose GeoAD earlier, but the paper really stresses the importance of using a realistic scenario over those synthetic benchmarks. Why was that so crucial?
Their main point is that those synthetic benchmarks, while useful for some things, often don't capture the dynamic complexity and those subtle behaviors that you find in real enterprise networks, especially ones running Microsoft Active Directory. Things like the small variations in how password spraying might work or fail because of account lockout policies, the unpredictable nature of a lot of exploits, or even the normal, legitimate user activity that an attacker could take advantage of those things are often either oversimplified or completely absent in synthetic environments.
So the inherent messiness of a real network actually plays a vital role in evaluating these automated attack systems.
Absolutely. They argued that even a slight difference in a password attempt can mean the difference between success and an immediate account lockout in a real system. Synthetic benchmarks often don't model those tiny variations accurately. Similarly, a lot of exploits have a low chance of working and can even crash the target system, which can have a ripple effect on the attack. Synthetic environments frequently miss these nuances. They also point out the importance of what they call abusable background activities, like users accessing shared files or network resources, which create opportunities for attacks like token capture and lateral movement. These temporal patterns, how things happen over time, are critical in real networks, but are often missing in synthetic benchmarks. So by using GOA, they wanted to test their prototype in an environment that truly reflects the challenges and opportunities of a live network.
Okay, that's a strong argument for using a realistic testbed. So they've got this environment and the LLM-driven prototypes. How did they actually assess its performance? What kind of data did they gather and how did they analyze it?
They used a two-pronged approach. First, they did a quantitative analysis, which means they looked at metrics, numbers, things like how many commands were executed, the timing of different actions, and the overall success and failure rates. This gave them a statistical overview of how the prototype was performing.
So the hard numbers, the objective data, and what about the other part of their analysis?
The second part was a qualitative analysis. They had 3 cybersecurity experts review the detailed logs, all the command outputs, and the context surrounding each action. These experts used a method called thematic analysis to identify recurring patterns in the data, such as any missed attack opportunities or unusual behaviors from the LLM. They also mapped the LLM's actions to the MIT, EATT, and CK framework to see how well they aligned with known attack tactics and techniques. And importantly, for each step, they identified both the accounts that were successfully compromised and potential leads, vulnerabilities, or bits of information the prototype found but didn't immediately pursue.
So a combination of the hard data and the nuanced insights of human security professionals to get a complete picture. Now, the big question, did it work? Did this LLM-powered system actually manage to compromise accounts in the Active Directory environment?
Yes, it did. The research showed that in every single run of their prototype, at least one Active Directory account was compromised. Across all their experiments, they fully compromised 5 unique domain accounts.
Wow, that's a pretty big deal. What about the efficiency? How many steps did it typically take to achieve that?
They measured the average number of planner rounds, which represent updates to the high-level strategy, and executor rounds, which involve actually executing commands. On average, there were about 45 planner rounds and roughly 4.7 executor rounds for each planner round. They also looked at the number of individual commands, which averaged about 4.6 commands per executor round.
And how accurate were the commands themselves? Did the LLM make a lot of mistakes?
Interestingly, they found a fairly high percentage of invalid commands being generated, around 35.9%. These were commands that either weren't valid on the Kali Linux system or had the wrong parameters.
So it wasn't perfect, but it still managed to achieve its objective, even with those errors. That's pretty impressive. You mentioned compromised accounts. What exactly did they consider a compromised account?
Their definition was quite strict. It only counted accounts where the system managed to extract the plain text password or successfully exploited Kerberos or NTLM hashes to perform what are known as pass-the-hash attacks.
So no superficial wins there. And what about those leads that the human experts were looking for?
On average, they found about 6.5 leads at the end of each run. These included things like accounts with Kerberos tokens or NTLM hashes that hadn't been exploited yet, low privilege access to services like Microsoft SQL Server, writable network shares, or signs of potentially exploitable vulnerabilities like Print Nightmare or misconfigured Active Directory certificate services. These leads suggested that there were more paths the prototype could have taken to potentially cause even more damage if the tests had continued.
So even when the testing stopped, it had often set the stage for further attacks. Now, one of the interesting aspects of this is the cost. Human penetration testers are expensive. Did the researchers look at the cost of running this automated system?
They did. They meticulously tracked their token usage with the OpenAI API to estimate the cost. They reported an average cost of $17.47 for each fully compromised domain account.
That's surprisingly affordable. How does that compare to hiring a human penetration tester?
Well, they compared it to average penetration tester salaries and the hourly rates charged by penetration testing firms, which can range from $100 to $300 per hour. Their conclusion was that even with their initial prototype, the cost per compromised account was very favorable. This suggests that LLM-guided tools could potentially reduce the amount of time needed from human testers, which would lower the overall cost. They even raised the possibility that this could make sophisticated penetration testing more accessible to organizations that typically can't afford it, like nonprofits and small businesses.
That would be a game changer, making those security assessments more widely available. They also analyzed which tools the prototype used most often and any challenges it had with them. What did they find?
They discovered that the prototype used a variety of command line tools, 72 different ones in total. The most frequently used included tools like encxc and netexec, those are for interacting with SMB and LDAP, SymbiClient for accessing network shares, cat and echo for basic file manipulation, and nmap for network scanning.
Oh.
They also saw frequent use of tools for Kerberos attacks and password cracking, like ImpacketGetUser SPNs, John, and Hashcat.
A pretty typical toolkit for this kind of assessment, but you mentioned earlier that there was a fairly high rate of invalid tool calls. What kind of errors were they seeing?
They grouped the errors into two main types. Type 1 errors were straightforward parameter errors, like forgetting a required parameter, which the tool would usually flag immediately with an error message. Type 2 errors were more subtle. The tool would accept the parameter, but it was semantically incorrect and cause the command to fail during execution. So, things like using cat with a file that doesn't exist or giving it an invalid IP address.
So the LLM sometimes struggled to use the correct syntax or provide the right values for those tools. Were there any particular tools that caused more problems than others?
Yes, they pointed out a few. Hashcat, the password cracker, had a really high failure rate, over 94%, mostly because of issues with the format of the password hashes it was given. They also saw lots of failures with ImpacketSwol-Client and Script-the-Client due to the use of incorrect subcommands.
Yeah, it highlights the challenges of getting an AI to really understand and use these complex command line tools. Now, to get a better understanding of the flow of the attacks, they mapped the prototype's actions to the MIRE ATT&CK framework, right? What did that reveal?
By mapping those tasks to MITRE ATT&CK, they could visualize the overall progression of the attacks. The top techniques they observed fell under tactics like credential access, discovery, and reconnaissance, with some activity in lateral movement. The techniques used most often were brute force, network share discovery, stealing or forging Kerberos tickets, and account discovery. This pattern suggested that the prototype was generally following a logical attack flow: gather information, try to get credentials, and then make some initial moves within the network.
Good to see that the attacks followed a recognizable pattern. The paper also mentioned some surprising findings and challenges they encountered. Anything that really stood out to you?
One of the most interesting things was the prototype's ability to carry out what they called inter-context attacks. For instance, it could retrieve files from accessible network shares and then actually analyze the contents of those files, looking for potential credentials. In one case, it found a PowerShell script with credentials in it and successfully extracted them. It even tried to analyze a plain text file and a secure string password in another script, though wasn't entirely successful with those. This kind of unstructured data analysis, where it's going beyond just looking at file names or metadata, is pretty unusual for traditional security scanners.
It's like it's actually understanding and extracting information from the content. What else surprised them?
Another surprising thing was that the prototype generated password suggestions based on the context of the target environment. The usernames in their Go8 setup had a Game of Thrones theme. The LLM actually came up with password suggestions related to that theme, like Breaker Off Chains 2022 for an account named Daenerys Targaryen. It shows a level of understanding that goes beyond just brute forcing with generic password lists.
Pretty clever, picking up on the theme and using that to its advantage. What about the planning and sequencing of its attacks? Did it show any smarts there?
It did. The planner was able to create attack plans with a logical flow, like performing ASREP roasting, then using password cracking tools on the captured hashes, and finally using those cracked credentials for further attacks. It also showed that it could manage those time-based dependencies. For example, to avoid locking out accounts during password spraying, it would split the user lists and mix in other tasks between attempts. If it did detect an account lockout, it would often add a task to retry that account later on.
So it wasn't just blindly executing a linear sequence of commands. It could adapt and manage its attack plan over time. Did they encounter any downsides or challenges?
One issue they noticed was that the planner could sometimes get stuck in a rabbit hole, focusing too much on one particular attack path, even if it wasn't working. For example, it might spend ages trying to emulate PowerShell's secure string or trying to crack very strong service account passwords, potentially missing other, more promising leads within the time it had. They suggested solutions like a circuit breaker to force it to try other options, or even some human oversight to guide it.
That's a common trap, even for human attackers getting fixated on one approach. What about that high rate of invalid commands you mentioned earlier? Did they dig deeper into the reasons behind that?
They did. They identified a few factors. Sometimes the executors simply didn't give the tools the mandatory parameters or used the wrong syntax. There were also mismatches between what the planner thought the tools needed and what they actually required, especially when it came to things like username or hash formats. Occasionally, it seemed like the necessary information wasn't being passed between the planner and the executor correctly. For instance, the planner might tell the executor to crack a hash, but not actually provide the hash itself. They also observed the executor trying to run interactive commands or commands that needed a graphical interface, which their setup couldn't handle.
It's a reminder that the LLMs need a much deeper understanding of how these tools actually work. But despite all those issues, the prototype still managed to succeed. How did it overcome those errors?
This is a really important point. They discovered that the prototype had some impressive self-repair capabilities. At a lower level, the executor would often retry a command if it got a helpful error message. Sometimes it would even correct the syntax or parameters on its own. For example, it figured out the correct parameter for specifying the target in LDAP search after initially using the wrong one and getting a help message. It could also detect if a tool it needed was missing and install it automatically using package managers like apt or pip, or even by cloning the code from GitHub. At a higher level, if the executor couldn't solve a problem, it would report back to the planner. The planner, with the help of that more advanced O1 model, could often suggest alternative approaches or corrections for the executor to try in the next round. This ability to recover from errors seems to have been key to its success.
That's a fascinating finding that even with a high error rate, the system could often get itself back on track. Finally, they discussed whether better tooling support could further improve the prototype. What were their thoughts on that?
They suggested that giving the prototype access to an attacker-controlled Windows VM would be a significant improvement. Many powerful Active Directory penetration testing tools are built using PowerShell and work best in a native Windows environment. They also talked about creating custom attack-specific functions for the executor LLM. Instead of trying to generate raw command line instructions, the LLM could call these predefined functions that handle the intricacies of specific tools. These functions could have better parameter handling and error feedback. They gave the example of how the LLM switched from trying to use OpenVAS, which it wasn't allowed to use, to Nmap with its vulnerability scanning scripts. They also talked about how it used JQ to analyze Bloodhound data because it couldn't use the graphical interface. And they specifically mentioned that a dedicated password cracking function could address the problems they had with Hashcat and John. So, making the tools more accessible and easier for the LLMs to use could really boost their effectiveness. To wrap up our deep dive, what were the main takeaways from this research? The biggest takeaway is that autonomous LLMs can indeed carry out assumed breach simulations and successfully compromise Active Directory accounts in a realistic environment. And surprisingly, the cost to do this with their prototype was comparable to hiring a professional penetration tester.
That really highlights the potential of this technology. What are the broader implications, in their view?
They emphasize the potential for making penetration testing more accessible. If these automated tools become more refined and easier to use, it could enable organizations with limited budgets to conduct valuable security assessments that they might not have been able to afford before.
It could level the playing field in terms of security testing, and they revisited the challenges and strengths they observed, right?
Yes, they acknowledge the main challenges, like the high rate of invalid commands and the tendency to get stuck on a single attack path. But they also highlighted the strengths, like the system's adaptability, its ability to understand and use information from different sources, and its surprising ability to fix its own errors.
And this research raises new questions for the future, doesn't it? What were those?
They asked two main questions. First, how do we detect and defend against these LLM-driven attacks? They noted that the attack patterns they saw were often similar to those used by human penetration testers. This suggests that existing defenses, like keeping systems patched, disabling old protocols, and using honey tokens, could be effective. The second question was whether LLMs could also be used to automate defenses and proactive security measures, maybe even to implement recommendations from penetration test reports.
That's an intriguing thought, using AI for both offense and defense. As we wrap up, what's one final thought you'd like to leave our listeners with based on this research?
I think this research forces us to really think about the future of cybersecurity, especially as AI becomes increasingly powerful, both for attackers and defenders. Organizations will need to carefully consider how they adapt their security strategies, the tools they use, and even the skills of their security teams to deal with this changing landscape. Things are evolving rapidly, and understanding both what AI can do and its limitations in this domain is going to be critical moving forward.